Hello everyone, very good evening to all. Welcome to Pantechelearning. Welcome to workshop of System on Chip and System Verilog for verification. In this session, we are gonna see a System on Chip architecture and what is the System Verilog audio description language. So basically, if you want to write the audio description language, there are many languages like Verilog, VHDL, System Verilog. These three languages are using to write our description languages. So in this workshop we are going to see the syntax and what is the purpose of system Verilog, what is the difference between Verilog and system Verilog, what are the added features between the compared to Verilog in system Verilog, and what is the test bench, what is the architecture of test bench, what is the purpose of the system Verilog test bench, how we are gonna use the test bench for verifications. So basically, system Verilog are used to write a design code as well as a test bench code. So before going to that deeply, firstly we look about VLSI. So people may know that VLSI stands for very large scale integration. It's the process of integrating millions of or billions of transistors onto a single silicon chip. So this is the VLSI on technology. It is a process of building a n number of transistors onto a single silicon chip. So by this technology we can achieve the high speed, as well as we can reduce the hardware size of the computer or any devices. So if we want to reduce the hardware devices, the main things is VLSI technology. So this technology is used for mainly reduce the hardware size and increase the power and also decrease the power consumption of the device. So these are the main three things our VLSI technology are doing currently. So before going to that, I want to show one thing example for what is the main purpose of VLSI. So you can see this picture, the person doing some wiring of some device, some computer. In this picture is like is taken from at 1980s or 1970s on that period. So on that period, the VLSI is a initial staging process. So we know that on that period, the whole room size which takes to make a one computer. But now you can see the very small in size, comfortable. This changing, this like you can see it requires a huge hardware, but it requires very less hardware size. So these technologies, this evolution is based on VLSI only. So by using the VLSI technology, we can build the n number of transistors. Like now currently we can achieve up to, I think, 3 trillion transistors are built in a single silicon chip. It's done by NVIDIA. NVIDIA is a big company. They are giving the GPUs for they are giving the GPUs for all the computers. So NVIDIA is a major company who giving the GPUs for other companies like Intel, Qualcomm, or Snapdragon, so on. All semiconductor companies, they are making the ICs like a processor like a Intel i7, i5, but they are depends on NVIDIA only. Why? Because of NVIDIA only one company will giving the GPUs to other companies, to other processor companies. So before going to the session, there is a one law, like a Moore's law. Is a scientist he said like every 2 years the count in the single silicon chip of transistor, it will doubles of every 2 years. Likely he is saying every 2 years the count of transistor in the chip or silicon chip, it will doubles every years. Like if you are in the 80s 90s or like 1990s, the size of the single silicon, the count of the single silicon is like a 10 lakh or something 20 lakhs transistor it have. But nowadays we have millions of billions of transistors in a single silicon chips. So is saying of a double the years it's currently achieving, and also we can also doing same that only like every two years we can build the double the rate of the transistors in the single silicon chip. So this is a main point you are saying Moore's law. So and then now see what is the future of a semiconductor industry in India. So now now we are in a poor state in semiconductor industry by compared to other states, other countries like Taiwan, China, America. So now India have a plan. So in coming March 13 or in coming 2026 or 2030, we are going to build a 3 factories like a frames to make a say ICs. So in by comparing the other countries, India is a major country. uh, we are importing the ICs. See, we are majorly importing the ICs from Taiwan or America. So we plan to build a frames in India to make our own ICs, to make our own chip, with tie up with Texas, with tie up with Intel or Qualcomm or Snapdragon like that. So if you take the VLSI as a career, you can easily grow up in future days. Why? Because of in the market, India will become the second largest semiconductor industry in future. Why? Because of Taiwan was only one country. They are giving the 75% of ICs to over the world. Like America also some having some factories, but they are not giving that much of ICs to the world. But Taiwan is the only country they giving the 75% or 70% of chips to the world. So if you like taking the example of the companies Texas Instrumentations, the Texas Instrumentation companies are giving the most number of ICs for Intel, Qualcomm, ARM or Mac. They have their own factories. They can build the ICs. They can export to to around the countries. So India had the same plan to make a 3 factories in India. Let's see what happen. I think if the India were done this, it will helpful for our youngsters whoever taking the VLSI as a career. It will very huge healthy thing for students or that candidates. And then why VLSI? I already said no. VLSI is main thing. Why VLSI is to reduce hardware size, increase the performance of chip, and then reduce the power consumption of the IC. So these are the things very important in VLSI. So you can see the cost effective, improved performance and speed, reduced power consumption. This all comes under the main purpose of VLSI. So and then I'm going to announce one things. Coming March 10, we are going to start the master class, 21 days master class on Intel Altera FLK FPGA board. This master class fully based on system Verilog and then FPGA board. How to use FPGA board, what is the Intel Altera FPGA board, and what are the benefits while if you take a FPGA course, what are the benefits, what are the knowledge you are getting, and then how to write a RTL system Verilog code, and then how to simulate the RTL code, and then you can do some projects in this master class. You will get the major projects like UART or I2C, these protocols, how to and you will get the basic knowledge to advanced knowledge about VLSI field and semiconductor field. While if you attend this master class, it is free only, it is open source. You can join in YouTube live sessions, and you will have a attendance on daily purpose. It is for attendance for it is a certification course. It is a 21 class masterclass, you will get a certificate at the end of the day. So it is will if you want to start your career in VLSI field, this masterclass will be helpful for you. And this in this masterclass we are giving the real time projects, and then we are giving the demo on YouTube classes. So with FPGA board. So then let's see the design flow of VLSI. So before going to enter into VLSI field or semiconductor field, you must aware of this design flow. So how chips are made, how the processors are made, how the memory, RAM, or how the any semiconductor device like if you see the one single silicon chip, it having the n number of transistors inside the silicon chip. You must have to aware of this how that chip are made. So firstly, we have to write a we have to make a specifications. So specification means system specification is nothing but how much of the core processor. If you take in any processor like a Snapdragon or Apple A15 SoCs, we have to design a black diagram. So how many cores it have, how many memories it and how many memory elements it having, and what are the DSP processors we are going to use in single silicon chip. So this much of specifications like what is the purpose of the processors. Some processors are using for specific task, some processors are using for general purpose processors. So Intel i7 Intel processors, Intel i series processor are general purpose processors. So each they are different between the processors. Like if you take an AC or washing machines, they are having some controllers. So controllers need some ICs like a chip. So these things also comes under the VLSI only. So not only to make the computer processor or phone SoCs, phone processors, we can VLSI is fully based on controllers. You can take Arduino board or any other node MCU. If in the wherever you see the ICs, it fully based on VLSI technology. This it follows this design only. So we have to aware of this. Firstly, we have to design system specification. So what is the purpose of IC? How many logical elements it must contain, and what are the peripherals it have to interface with the real-time devices, and then what is the memory sizes is required, and then how many GPIO pins like a general purpose input output pins it must contain, and then what is the clock period, and what is the clock pulses, and then how many and what is the clock oscillator it must have to perform high speed computing. So these are the techniques, this are the specification we need to decide, and then we have to make one black diagram, and that black diagram is it must be in small, it must be very less in size. Like less in size means the black diagram will give the architecture of the IC. So I will show in upcoming slides. So and then architectural design, and then functional design and logical design. So this is the in this functional design and logical design comes under the RTL engineer. So RTL engineer is nothing but they are writing the RTL code, Verilog or system Verilog code based on the required specifications, and then they are writing the logic design. So for transmitting the data inside the chip, they are using some AMBA protocols like APP, I2C, like that. So they are writing that kind of design code, and then how much of data will send or receive in a particular bus. So these things or logics comes under the functional design and the logical design. And then circuit diagram, this part, and then this stage comes under front end engineer. So basically we can divide the VLSI semiconductor engine, we can divide this into two parts, like a front end engineer and then back end engineer. The front end engineer will do the design specification, writing RTL code, and then they have to test the RTL code, and then they have to make a circuit design. This part comes under the front end engineer. Front end engineers, it means designing the in front end engineers we have two engineers like RTL engineer and then verification engineer. So RTL engineer will write the design code for the required specification, and then verification engineer will write the system Verilog test bench or UVM test bench to verify the RTL design, to verify the design. So we have to write the design code, and then we have to write the test bench code. We have to make sure our all the test case will pass. If there is any error, any bug means it will be very huge loss of our company. Why? Because of if there is any bug means we cannot we can't recode or refix the bugs while making the hardware. Why? Because of if you taking a software, we can fix the hardware. Sorry, we can fix the issues while after the simulation or after the completion of the software project. But in the semiconductor industry, if you complete it on ICs, we can't refix the errors. If you make it on IC, if you want to change some things, you can't change after the making IC. Why? Because of we make it hardware, we can't change or we can't make alteration in hardware. So for that, testing is very important. Testing the hardware, testing the RTL code is very important. Testing the design code is very important. For that, we are using system Verilog for verification. So these things are physical verification and sign-offs, layout, post-processing, fabrication, packaging, and testing. This all comes under the physical design engineer. The physical design engineers will taking care of the ICs. IC means how much power consumption it's occurring, or what is the size of the ICs. Though we people may know that a nanometer technology, 3 nanometer or 8 nanometer, 7 nanometer technology, the size of the IC, we have to fix the all logical blocks or all logics inside the specific nanometer. So if you're making the 3 nanometer IC, we have to build the whole logical block in the size of 3 nanometer only. So these techniques comes under the physical design engineer. So these are the steps like a partitioning, floor planning. Floor planning is nothing but making the memory blocks or DSP blocks, counter block or GPU block inside the assigning. They are planning to in which in the chip which part it must be contained. Like I will show in the upcoming slides. So you can see here, this is a chip. The physical design engineer will choose where the GPU will come, where the memory card chip will come, where the big CPU will come, where the NOC will come, where the in this chip, inside the chip, they are assigning the blocks where it comes like a DSP. They are choosing the appropriate correct spot or correct place inside the chip to make the communication easier, to reduce the size of the chip, to make the build the n number of transistors in the chip. So these things comes under the physical design engineer. So this is a design flow of VLSI. So let's move on to what is we know that HDL is nothing but auto description language. Is used to write a structural or behavioral of digital circuits. So it's nothing but RTL code, register transfer level code. We can write this hardware description language by using Verilog, system Verilog, and VHDL. And then let's see some sample code. So I'm going to write a simple system Verilog code for full adder. So writing a Verilog code is it's not that much difficult. we can, if you know C++, it's easy for you. So Verilog and system Verilog follows the same conditions or functionalities of C and C++. So there is a only difference between syntaxes and the data types. If you compare the C and C++, the different things is syntax and the data types and the purpose. In C and C++, we are writing for high level functionalities, but in system Verilog we are writing for circuit level logics, like hardware logics, like conventional circuits, sequential circuits, digital circuits. So we are writing for that only. So the basic syntax of the system Verilog code is, first we have to write a module and then we have to write a module name. So I am writing full adder, and then full adder. This is a basic syntax, module syntax for system Verilog. For this simulation, I am going to use EDA Playground. So there is a one simulator in you can find in, it is an we can run this in Chrome or any website or any browser, any any engine. So if you want to access this EDA Playground, you have to log in with your companies or schools or college institution by using the institution mail. By using the institution mail only, you can use this EDA Playground. We can write in this EDA Playground, we can write a design code. So you can see here, this part is used for design code. You can see a code your design here. So this part is used to write a design code. This part is used to write a test bench code. So I'm going to write a code for full adder. So inside the bracket we have to write a port list. Port list nothing but input output of the digital circuits. So before going to start a code, I want to show one thing, circuit diagram for full adder. So these are the inputs and outputs of full adder. The inputs are A and B, C in, carry in, and then outputs are sum and carry. So if you are aware of the logical expression like this, based on the logical expression and based on the behavior of the full adder, we will write the design code, like we will write the full adder code in system Verilog. So this is a full adder logic circuit. If you take in sum means the equation will come by A XOR B XOR of C. So if you want sum, we have to write a logic of A XOR B XOR C in, like a carry in. So A XOR, here you will get A XOR and B XOR, and then here you will get a XOR B XOR and A XOR B XOR XOR C in. So here A XOR B, here A XOR B XOR C in. So this is a sum equation, and here you will get the A and B, B and C. So I will write the logical expression in a code. So here you will get the expression of A and B are B and C or A and C in. So this is the equation for to get a C out, carry out in full adder. So you can also find in truth table what is the functionalities of full adder. So the main thing is full adder is nothing but adding 3 elements. So if you adding the 0 1, you will get at 1 as output. So you can see here 0 1. If you add this 2, 0 and 1 and 0, 3 inputs if you add means you will get 1. If you are adding the 3 A, B, C all are 1 means you will get the sum 1 and also carry 1. So if you add the 2 ones, 1 0 is 1, you will get the sum 0 carry 1. So it is the functionalities of full adder. So if you are adding the 2 ones in the 3 bit of input, you will get the sum 0 carry 1. If you are adding the only 1 1 in the 3 bit of input, you will get the sum 1 carry 0. So if you are adding the all 3, if you are adding the all 3 inputs of 1 1 1, you will get the sum 1 carry 1. So this is our logic. So I'm going to write the full adder code. For that, we inside the bracket we have to write a port list. So port list is nothing but input output signals in our design code. So input is one keyword, and then logic is a data type. Logic is data type is it having the 4 state A 0 1 X and Z. So in this workshop we can't give full explanation of what data types or system Verilog. We will see on upcoming slides or tomorrow workshop. We will see the syntax and the data types of the system Verilog. Now I am going to write a simple sample code for full adder. So inputs are A, B and C. These are the inputs. We are going to write the full adder code and then outputs are output logic sum and carry. So these are the input and output of our design, full adder design. So assign. So I will tell you tomorrow what is assign, and it's a data type or keyword. I will say tomorrow sessions. I can't tell you all the things in one session, so I will tell you about the syntax and the data types in tomorrow sessions. So and then here is this is a symbol for XOR in system Verilog. So A XOR, for if you want to some expression, you have to write A XOR B XOR C in, and then assign carry is one output, and then the equation is A and B. This symbol is refer as and, this symbol is refer as or. So you know that and means multiplication, and symbol is will do the multiplication operation. This or symbol, or means addition operation. So and then B and C in, and then A and C in. So this is the design code. This is a simple design code for full adder. So in this part we are writing the similar design code. We have to test that whether it's correct or not. For that we are using test bench. So module test bench, TB stands for test bench, and then end module. So in this test bench we are going to write a logic A, B, C in, and then logic sum and carry, output and input signals, and then we have to instantiate. The instantiation is nothing but making connection between test bench and design code. So in this test bench we are passing the stimulus to design code. So imagine this is the one IC, full adder IC. We are giving the inputs. The pins are A, B, C, and some one carry. These are the pins we are giving to input. So for that we are using the stimulus test bench. From the test bench only we are passing the stimulus means input signals to design code. For that we have to make connection between this module, test bench module, and then full adder module. For that we are going to use instantiation. Instantiation of design module. Instantiation is nothing but connection between the design code and the test bench code. So for that we need to write full adder module name of our design code, and then instance name. We can give any name, like I will choose A1. Inside that we are connecting test bench model having some signal, and then full adder design code having some signals, so input signals. So we have to connect each and every signal. For that I'm going to use dot A. So inside the bracket it will refers to current module. So outside of the bracket it will refers to other module. So if you given like here I am using the capital A, so I have to I have to change here capital A. So and then B, and then C in front of the every signal you have to give like a dot. So this one syntax required, and then sum, and then carry. So this is instantiation. So and then we have to pass the stimulus to design code. So for that initial begin end. So this is one block, initial begin block. Inside this only we have to give stimulus. So I'm going to write a stimulus for the design code, like A equals, firstly A equals 0. So I'm going to use this truth table. So I'm passing this. So I'm passing this stimulus. So I'm taking this truth table. A equals 0, B equals 0, and then C also 0 at the initial stage. So this means delay at every the initial means the simulation starting stage. At the initial stage all these three signals having the 0. After the 10 nanoseconds or millisecond, whatever you required time period, after 10 nanoseconds my inputs are A equal to 0, B equal to 1, and then C equal to 0. Sorry, we can give like a 3-bit binary. So C equal to 1. So after 10 nanosecond I'm changing the stimulus. So for that, for the time consider, I will copy this and paste here. Here 1. So I'm following the binary repetition of a 3-bit. So here one, and then here one, here 0. So it's enough, we will check the waveform. So and then $finish, it will finish the simulation. So if you want to check the waveform in the EDA playground, so we'll check by the $monitor. So $monitor is nothing but print statement. If you know C or Python, print, while if you want to print some things, we are using the print statements. Same thing in system Verilog, $display or $monitor. There is a difference between $display and $monitor. I will say in upcoming classes, upcoming workshops. So I want to see in output is A. So it will print as A in binary, and then B in binary, and then C in as in binary. So and then sum in binary, and then carry in binary. So I'm saying that A, B, C in sum and carry. All these signals I want C in binary forms. So I want to give respective variables A, B, C in, and then sum, and then carry. So I'm choosing these are the simulators. There are a lot of simulators like Cadence, Siemens, Costa. So I'm choosing the Siemens Costa. So I run this. Show to save and then run this. You can see here. So I am passing the emulates. I am passing simulation. In the starting stage of simulation, all the values like A, B, C in all having inputs of 0. These are the stimulus. A equals 0, B equals 0, Z equals 0. These things are stimulus. These are the outputs. So I am passing the stimulus. I am getting 0, 1. So and then 0, 0, 1. Sum, you will get a sums 1, carry 0, and then 0, 1, 0. You will get a sum 1, carry 0, and then if you are adding the 2 ones, you will get the sum 0, carry 1. Here it also having the 2 ones, so sum 0, carry 1. Here it also 2 ones, sum 0, carry 1. If I change here, if I change last one, like all the 3 inputs having the 1, 1, 3 ones, I will get the sum 1, carry 1. Yeah, you can see here sum 1, carry 1. So this is a way of writing the system Verilog code. In this in the upcoming master class, in the upcoming workshops, I will tell you what is the syntax and how to start from scratch in system Verilog. And then we are gonna see HVL. HVL is nothing but hardware verification language. So I already said no. System Verilog is through to write a system verification code. So same things. Here it having some test cases, assessment, functional coverage. These things all cover in my master class in upcoming in March 10 it will starts. And then you people may know that what is difference between CPU and MCU and SoCs. CPU is nothing but single processor core, but MCU is a single processor core, but is the main difference is a CPU having the external memory, external DSP, or external GPIO connections like that. But in microcontroller it having all these things like a DSP block, RAM block, memory block, counter block are inside the one chip is called controller, like a microcontroller. And then SoC is nothing but a system on chip. It contains all the things. So in microcontroller, in MCU, it won't have GPU part in the inside the chip, but in SoC it having the GPU part inside the chip. In CPU, if you take in your computer, you having the two processors, like a GPU, like a CPU and then GPU. Both are in separately, but in SoC GPU and CPU are inside the single silicon chip. They made in a single silicon chip is called SoCs. That the SoC chips we are using in mobile phones. All the mobile phones are based on SoC only. It having the GPU, DSP, peripheral device, camera interface, camera interface, or memory, flash memories. So these all things are comes inside the single silicon chip is called as SoC. It's like our whole system inside the single silicon chip is called SoC. So I already said no. A single silicon chip, it having memory interface, GPU part, modem, DSP, antenna, or 5G, 4G, LTE, and then AI, like that. If you using a 5G mobile, there is a block inside the SoC 5G block. So that block will do the performance of 5G requirements. What are the specification? What are the required decision making? How much of data how much of data transmitting, receiving? This all comes inside the 5G block in the SoC. So you can see here analog and RF. So I will show you in this. So before going to that, so all SoCs are if you take any mobile phones, Apple or Samsung or Redmi, MI, all these mobile phones, they are using SoCs. The architecture is owned by ARM. ARM is one company. They are provided. They have in the copyrights of the SoC architecture. The companies like Qualcomm, Snapdragon, MediaTek, Exynos, Samsung Exynos, they are using the ARM architecture. They have to buy the copyright, and then they have to do some modification in architecture, and then they will use the SoC architecture for our own SoC makings. So ARM is one company. They will give the architecture for SoCs. So in ARM architecture, it having AMBA buses. AMBA is nothing but one bus protocols. Inside the chip, the blocks must be contain the data buses or bus. The bus is used for transmission data one place to another place. So that they are using AMBA protocols. We'll see in upcoming classes. So this is the SoCs looks like it having GPU, memory cache, so DSP, little CPU, display engine, video processing, ISP, security, enclave, memory controller, analyze on GPU. So NOC is nothing but network on chip. So if you want to connect each and every, if you want to connect a GPU and a CPU and memory cache and GPU by using the NOC. NOC is nothing but network on chip. It will connect the each and every blocks inside the chip by using the protocols like AMBA protocols, interface protocols. So in the coming master class, I will tell you what is AMBA protocols, how to write a design code for AMBA protocol, and then example of the SoC mobile phone, Apple M3, Snapdragon 8 Gen, Apple A17 Pro. These are the NVIDIA Tegra X1 is a GPU. So in the automotive industry like Tesla, F30 chip, these are the chips and the SoCs we are going to use our day to life for AI and ML purpose. The Google TPU, Tesla, Tocho, D1. So these are the SoCs we can commonly see in your market. So this is one basic architecture of the SoC. This is a ARM based SoC architecture. So you can see here processor ARM Cortex M0 processor. So direct memory access, MUX. You can see here system RAM control. UART is used for interfacing the variable devices. VGA ROM. VGA is nothing but VGA monitor, GPIO, ROM timer table, 7-segment display, or watchdog timer, UART, ABB peripheral used for to connect the peripheral devices like a printer or any peripheral devices, and then clock generator. This setup is called as ARM architecture. If you want to connect those things by using the NOC, network on chip, the NOC is nothing but buses. You can see here this is a bus. It's like a ARM AMBA AHV bus, advanced high speed bus. So AHV is nothing, stands for advanced high speed bus, high performance bus. It can transfer the data very high speed between the these blocks to this block, like a processor, ARM Cortex processor, and VGA ROM, and then GPIO. So this bus protocols make sure the communication smoothly inside the silicon chip or inside the chip. So this is basic architecture of ARM SoC, and then this is also one architecture example for the SoC. So you can see here A7. These are the ARM Cortex A7 processors. So it having the 4 core processors. So if it having the, you can see here it having the only one core. One core means one processor. It having the 4 core. 4 core means it having the 4 processors, and then it having the A15 another 2 processors. So it having the 7 core processors. So each and every core processor it having one cache memory, L2 cache memory. Inside the every one core processor it having the L1 cache, and then it for in this block for 4 core processors it having the L2 cache memory. For this A15 processor, for this 2A15 processor it having the L2 cache memory. So cache memory is nothing but it's storing the data as you how to say, it is storing the addresses. The cache is basically storing the addresses. If you want to open something as a speed, if you want to open some tabs in your Chrome or in your mobile, if you want to open some apps very fastly, they will store the address of the memory in the cache. From the cache only the processor can send the instruction. They can make communication. They can make a data transfer fastly. So if you imagine the main memory comes here, like here. This is one chip. The memory block is in here. If you want to CPU access this memory block, it will take some time. So data will becomes here. Here it having the interface like AMBA protocol. So they come over the AMBA protocol and then they will come here. So it will take some time. If you store the whatever you required details in the cache, the processor can easily then the processor can easily attain this, or they can easily access the whatever user required. So if you for example uh, if you log in into some website, you have to write a mail ID. The login asks to write a phone number, mail ID, or something else, something data from you. But cache memory already having the memory address, and that address it having some mail ID number or phone number. So while if you enter that website, that website asks to you to write a mail ID to your mail ID. You can see some suggestion. Your mail ID will pop up you. So these things are comes stored in cache only. So cache memory will take some important data and then stored in memory, cache memory. Wherever you want the processor need that particular data, the cache will give that data. So for making the speed, the cache memory cache are using. So this is one example for SoC. Here you can see here PCI is used to communicate the GPU and the CPU, and then physical layer, the memory scheduler, subsystem interconnect, Wi-Fi module, GSM, LTE. So HDMI, MIPI is used to interface the MIPI camera, mobile camera, and mobile display interface, and then PMU, and then JTAG. So these are the logical elements are inside the single silicon chip. The front end engineer will decide where the CPU will come and where the IPs will come in the IC. So they can decide how much of a size we have to give for the CPU, how much of size we have to give for the processor cores. So these are the designs taken by front end engineer. The back end engineer will ensure that power consumption of these blocks. So if you're using the 5G or Wi-Fi, this block will consume the more power. If the chip requiring or consuming the more power in this block, the physical design engineer will have to reduce the power consumption of this block. So they also some doing testing and verification of power consumptions, size of the chip, and then they will give some conclusion. They will make some appropriate correct power consumption less processors or chips, and then they will complete the process of the fabrication of IC, and then we can buy in online, or we can use it in smartphones nowadays. So this is the architecture for one example for SoC. In these all things will comes under the SoCs, like in single silicon chip. So this is also an example for this is useful. This SoC is useful for how the AMBA buses protocols are used in SoCs. So you can see here AX7 protocol. It is used for high-speed data transmission or streaming purpose. So if using the mobile phone, I imagine you are going to you can give the live video and the voice or audio transmission for audience. If using the Instagram, you can go the live. On that time, you can access the camera logic, audio logic, DSP logic, filtering. If using some filter means they will perform DSP logic, and then you have to transmit through your 5G to the audience. So basically you are using all the parts of like a memory block, camera block, maybe display block, and then DSP block, and then audio block, and then 5G block. These whole things we are using at a times for we are using at the high speed of the time. So for that using high speed, these are the things like AXA protocols will works under that. AXA protocol is nothing but advanced accessible interface. It is used to transmit the data at high speed. So these things are inside the SOCs, and then these things you must have to know about SOCs. From coming tomorrow, we are gonna see a syntax and basic structure and what are the data types of the system Verilog. We will see in tomorrow sessions. I think this is enough for today. The SOC is not a simple topic. If you take this topic, it must require at least 1 week to complete the what is the functionalities of the SOCs, how the data transfer between the blocks, this block to this block, or memory block to processor block, how the processor will give the instruction for the memory, and then other peripheral devices, so other peripheral components or other peripheral blocks. So it will take up to 1 weeks. So we must aware of the Samba protocol, and then inside the single cell concepts we are having all the required elements for general purpose usage like camera, memory, MIPI camera interface, and then DSP, and then audio block, 5G, Wi-Fi, GSM module. So these things we must aware of this. So we'll see tomorrow. Thank you guys. Thank you for listening.